Good morning, Eamon Das is my name, and I hope you're enjoying the course. What's so special about what makes quantum computers so special? And today we're going to talk about complex numbers and imaginary numbers. We will touch upon complex conjugates and squared magnitudes. Obviously we can't do a complete course here in linear algebra and matrices and everything. So I'm just going to highlight the things that you will come across in quantum computation. But I encourage you to do further research. In fact, I implore you to do further research. Otherwise you will fall down at sometimes because it's so abstract. But what we're trying to do here is represent, let's just take one example, represent superposition in a mathematical way. Now, if you remember, we have, let's just say we have the nucleus, and then we have two orbitals around the nucleus, the ground state, where the electron is, the ground state and the excited state. We know for certain that the electron is in one of those two states. This is after it's been measured in the real world. So it's dead easy. If we know that the ground state is 30%, we know the probability that the electron is in the excited state is 70%. This is all easy because we're using real numbers, which we're used to. You've never heard of somebody saying there's a minus 30% chance of rain today. You never hear that because everything in the real world is between 1 and 100. And we know that the electron there's a 100% chance of it being in the ground or the excited state. So if you add them together, it comes to 1. So obviously if one of them's 30, the other one's 70. But when we talk about superposition, where the electron is in a quantum state of being in both orbitals, well, then we're lost, aren't we? I mean, where do you start? And this is where complex numbers come in. And an imaginary number is part of a complex number. It forms an ingredient of a complex number. But with complex numbers are very, very handy when it comes to quantum computation because they can represent physical states and transformation of physical states exceptionally well. They have a wonderful attribute that with complex numbers, no matter what algebraic expression you do to them, the answer will always be a complex number. And you don't get that with real numbers and rational numbers. Like I say, if you square, I was just about to say, the imaginary number always comes down to I equals the square root of minus 1. So there's a real number, minus 1. There's an algebraic expression, the square root, and we're lost. So real numbers don't hold their integrity, if you want to put it that way. And that's very important. You'll come across that later in quantum computation. So an imaginary number, I equals the square root of minus 1. It is not a real number. It doesn't exist in the real world. You can't have the square root of a minus 1 chance it's going to rain today. It doesn't exist. But as an intermediary step, it's very, very useful. So if we said, for instance, x squared equals minus 1, well, x squared, it means that we can represent that using an imaginary number, and then we can do what's called a correction factor on it to change the physical state into another complex number. The complex number always takes the form of a plus bi, where a and b are real numbers and I is an imaginary number. And the beauty of it is any complex number can be represented in this form. That's the beauty I was talking about. before, so it's exceptionally consistent. So the I is the imaginary part of the complex number. You've got A plus BI, A is the real part, B is the real number, but because of I, that's called the imaginary part. BI is the imaginary part, and A is the real part. And we can play around, which you'll see examples now coming on your screen. So what happens if we say, for example, x squared is the correction factor that we're looking for to change a physical state, to transform a physical state. We can then express that in imaginary terms using x. Now, superposition and complex numbers, the unreal world much prefers to use x, which doesn't exist in the real world. But as we can use it too, but as an intermediary to getting to x squared, you might need to multiply the correction function, square that, square x, and then you've got the correction function squared equals negative square root of -1. And it gets obviously far, far more complex than that. But basically what I'm saying is they're useful as an intermediary. I'll now give you a few examples, which I'll talk you through. And I'll talk you through complex conjugates, which are a wonderful, it's so easy. Basically, it just changes the coefficient. So if you've got the coefficients of the imaginary part of the complex number. So if you're A plus BI, the complex conjugate of that is A minus BI. I'll show you that in a second. And why we want to know that is that you can then multiply them. It helps when you want to multiply them together, divide them, because we have to manipulate all these different states. And the beauty of it is then, imagine, and we always remember what we're doing and why we're doing it. Because we're now mapping out on a qubit, we're able to give more physical states, an infinite number of physical states actually, or n. So you've got 2 to the n. So the number of qubits you have equals n. And the number of qubits you have, the number of physical states you have, is 2 to the n. So that's 2 to the exponent of n. To give you an idea, if n equals 300, then 2 to the 300 equals all the atoms in the universe. Think about that. If you scrape a little bit of dirt from under your fingernail, that little bit of dirt's got billions and billions and billions and billions and billions of atoms. And we're talking about a quantum computer with 300 qubits can be able to map it out because of complex numbers and because of superposition and entanglement and tunneling. So we can instantly say whatever's on this qubit, it's on another qubit. And we can create gates, just like logic gates for digital computers. We can create quantum gates where we can then put qubits in superposition, do all these wonderful, wonderful calculations, but we can't look. We can't measure them, because if we measure them, it collapses the wave function, which you know a little bit about now. But you can see where the power is coming from. I hope you enjoy the